today we're gonna get into basically exploits, obfuscations. So we'll dive deeper into some of the PDF content that I talked about. I think before we went into the sessions about assembly language and everything. So this ends up being probably one of the bigger areas of malware analysis. So you end up analyzing a lot of the documents or a lot of the attachments, a lot of the files that will typically be what's transmitting malware, or I should say transmitting an attack to a target. So those of you remember the mock attack that I set up back during the beginning of class that involved the PDF or whatever, and that sequence of steps, or I should say that pattern, that attack pattern is very common, is getting to be a lot more common nowadays as individuals end up, or I should say end up being separate from a lot of the data they work with. Stuff moves to the cloud and everything. We're going to talk during this lecture about a large number of techniques and features that are in PDF documents. Some of these are a little bit old hat. They are techniques that were a lot more commonplace on older versions of Windows, on older versions of Adobe Acrobat Reader and things like that, but they're very useful they're very useful as examples to work on because with a lot of attacks, say targeting non-PCs, targeting Internet of Things infrastructure and control systems and all the other stuff like that, you're likely to run into this style of attack. So also, these end up being a lot of really good examples to try and hone the reverse engineering and malware analysis and basically what amounts to uncracking skills on. So I'm going to focus on PDF documents, and I've kind of bounced it up in the air as to whether I'll go back to, say, documents again, or what I might do, and this kind of depends upon what material I get. So either I can go broad and I can cover a lot of different attachment types, or I can dive deep on a handful of PDF exploits, and we can drill down to how those actually operate on the system in the next class. And it's just kind of going to be up to, I don't know, mostly up to the example sets that I find and what's valuable. So this lecture I'll start off with the PDFs. We're going to talk about specifically obfuscations, so attempts to conceal the attack. So we talked through some very basics about how attacks will get transmitted via PDF, and we even broke one out on one example of them. Many of those things required very few steps for us to unwind some aspects of the attack. So we'll talk through some of the features that exist in PDF that allow you to try and conceal that. We'll also talk through some exploits, kind of how those in general work, a really common attack pattern, and look at a couple of example documents as well, hopefully, if we have time. And then what's called shellcode, or generally speaking, is native assembly language you have embedded in your document. So usually the goal with, say, a PDF that you're trying to attack with is that you have some sort of embedded executable code in there that you want it to execute. And if that's native code, so if it's supposed to be like CPU native code, there's a common term called shellcode for it. So I don't exactly know the etymology of that name, but that's the term that everyone uses. So I just have it here for reference as well. So we talked through a handful of the basic obfuscation techniques. Sorry, just take a seat. we explored some of the basic obfuscation features that exist in earlier talks. So if you remember, when we were looking at one of the PDFs that had JavaScript in it, if I remember correctly, the stream, the raw stream data that was inside the PDF, you couldn't see the JavaScript. It wasn't until we actually ran it through a deflate filter. That PDF parser has some built-in functionality for auto-recognizing the filters and then auto-applying them if you choose. So those frequently are used as a way to try and hide what you're doing, just like in that document it hid the JavaScript from us. There is also a number of other features that facilitate obfuscation. So there's stream filters, just like I said. There's also stream or string encryption, and I'll get to that a little bit later. It's not exactly what you would expect. There's also what I call alternatives, or almost like homoglyphs or whatever. Basically name encoding and string encoding alternatives. So we'll get to those. And then, like I mentioned with the Visual Basic macros, and I also touched on earlier on with the PDF stuff, is runtime JavaScript expansion. So because you have full JavaScript interpreter in there, you have all the features and functionality that come around with a full programming language and programming environment. So you can do whatever you want with that. So one of the more common ones that we see a lot is name and string obfuscations, and this is the PDF format again. So it supports a large number of features that are intended to allow you to make the document either be more readable or support characters that you may not be able to type on the keyboard. So a great example might be some of the international characters or even some control characters and stuff like that. So if you remember, there's I think I can't remember exactly how many there were. There was a finite set of object types in PDF. I think it was less than I could count on my fingers. One type of those was name objects, and was almost like how to define entities with a particular name or something like that, or define variables, that type of thing. So using the name objects is how we're able to tell, say, some parts of Acrobat Reader how to present a page, or possibly how to run code, or what to do during a particular action or something like that. So it's almost like how it's one way that's used for hooking JavaScript up to certain document viewer events and things. Another example of it is how to embed a table of contents or something like that, or thumbnails into your document. So one of the features that it has, don't ask me why, but it has it, is the ability for you to arbitrarily, if you want to, you can overwrite all of or some of the characters in any one of these names with hashtag or pound, number, hexadecimal number. So this is 55 hex. So, whatever 5 times 16 plus 5 is. So in this case, you can replace the U and the I with these hex codes. So this gives you a decent number of permutations for being able to rewrite, say, very simple attacks using these substitutions that can be unpredictable. So it would be very difficult for you to, for instance, write a search or grep or find or something like that to try and look for this. You'd have to look for every single permutation. So as this is a really simple string, but basically you have, I can't remember if it distinguishes between upper or lowercase, but hypothetically, if it doesn't distinguish between them and it needs to be uppercase, then you end up having 2 times 3 different permutations of this one, or probably more than that actually. So yeah, or sorry, 2 to the power 3 permutations, I think. So like 8 permutations. So you can arbitrarily do that, and that means that if you want to try and look for, like in this case, anybody trying to use the URI keyword in a certain spot, you may have up to 8 different strings, literals, that you're trying to look for. So it complicates, your analysis as a defender. One of the features that's in that PDF parser, and we'll see that this occurs. This is a very common approach. One of the features in that PDF parser is that it will go through and it'll parse these things just like the CPP parser parses your C++ code for you before you send it to the compiler. It'll parse the document and turn it into a more normalized form, so that if you want to look at the output from the PDF parser and look for your attacks in there, then you can work with a much simpler, more controlled set of data. Also, string data. So if you remember, any string objects are defined in this way. There's actually 2 ways to define strings. So this is one of them, where you enclose the string in parentheses. But also you can define an arbitrary string of bytes using hexadecimal values as well, as long as you bracket it with the less than greater than instead of the parentheses. When using this form, you can actually use any arbitrary amount of white space, and this allows you to embed really long strings with arbitrary characters in it. And you can, separate the characters in whatever form you like, so it gives the author a lot of flexibility. But with that flexibility the author gets, you get a lot of extra pain from having to be forced to look for all possible different variants, which this ends up becoming something where there's a nearly infinite number of variants to this format, and likewise this approach as well. So there's a number of different encoding mechanisms that strings support, and this is like any string within there. So for instance, if you even just wanted to put together a document that said, hey user, click this link right here, that link would be rendered from a string typically, and so even if you weren't trying to launch some sort of advanced shellcode attack or something like that, you could still obfuscate the link that you're trying to get the user to click on that's in there. So the 2 major ones that I've seen, and as I said there are others as well, the 2 major ones I've seen are being able to use white space. So this is white space similar to if any of you have ever written like a shell script or something. A lot of times you may have run into this, and you may not have. But if you haven't, if you want to have a really long command that you're trying to run that has like 30 or 40 arguments to it or something like that, if you put a slash like this at the end of the line, then it allows you to continue. So from there it'll actually pass over the new line plus all the white space, and it'll merge the next line onto that one. So you can have or you could list your single line command in multiple lines of a shell script, like in Bash or something. So it's basically called it's frequently called a continuation character. So this allows you to basically have HE and then continuation LLO, and this right here is functionally equivalent to that, and actually all 4 of these are functionally equivalent to one another. So there's 4 different approaches that I've listed here. And then the other one is similar to what was done up here with escaping certain characters within, within the name. I can arbitrarily escape certain characters using the octal number instead of the hexadecimal number for some reason inside of here. And my guess is that those 2 features were probably authored independently of one another in the Adobe program code or something like that a long time ago, which is parallel evolution but completely separate paths. So this pretty much gives you nearly infinite possible recipes for carving up your string data and everything like that. and making everything very, very hard for someone to analyze. So I won't dwell too much on those types of things, but I did want to highlight them because there's something you run into very frequently. And a lot of times, in order to get to the next step, in order to get to the point where you want to analyze the executable code, a lot of times you have to pass over one of those barriers first. So the next one that I'll go to is the one that we very lightly touched on before, but it actually works a lot more deterministically, or it's a lot simpler. It's a lot more straightforward than the ones I just showed you, and that is the stream filters. So the stream filters are basically filters that the entire block that's between the two stream, the stream and the end stream keywords in your PDF is supposed to be passed through one of these filters. So for each one of the filters, the blob that it's working on is guaranteed to fully be decoded or expected to be decoded by one of these filters. One of the curious characteristics of it is that you can actually apply these one after the other, so you can actually apply these in arbitrarily long sequences. Or if there is an upper limit, I have not seen it yet. So I could, for instance, inflate encode, so I could use a zlib compression on my data, and then I could also apply an ASCII 85 encoding to that, and then I could come back and inflate encode it again, and then ASCII 85 encode it again. So I could come and basically create this shell, upon shell upon shell upon shell of encoding around it. So I can arbitrarily pick those things as many times as I want, as far as I can tell. So as I said, there might be some sort of upper limit to that. If there is, I don't know what it is, but that's worth keeping in mind as well. Again, I think that trying to unwind that loop is also something, or I should say trying to unwind that all the way down to the root node is something that that PDF parser tool that we looked at has a lot of code in there to do for you. And also one of the other key characteristics here is that when you're looking at the object data, so if you remember, you end up having like an object declaration followed by a series of names and strings and stuff like that that basically define the object, and then following that you have the stream data. Within that first object declaration or object definition, you actually have defined all of the sequence of filters that are going to be used. So you don't end up in a situation where you unpack it and then you find out that you need to unpack it with something else, and then you need to you already know what the sequence of steps is going to be before you get to read the first byte of stream data. So one of the other interesting characteristics is that PDF supports what's called passwordless encryption scheme. And really what this is intended to provide is if you've ever gotten a PDF document where, and this is an older feature, I believe it's implemented differently on newer versions of Acrobat Reader, but if you're using Acrobat Reader and you have a PDF document, you can't select text and use the copy feature on it, like it looks like it's grayed out or disabled. In PDF, the spec actually implements this passwordless encryption scheme. I'll put encryption in like big air quotes for you. It basically means the key to decrypt the data. So the data is all encrypted, but the key to decrypt the data is also embedded within the document somewhere. And it's not really supposed to be a foolproof method, or a comprehensive method, I should say. But it's supposed to prevent, for instance, you from being able to get like an ebook and then just anyone being able to print it out on a printer or something like that, or copy paste the text into Word and then print it into a printer or something. So frequently something implementing this passwordless encryption scheme ends up not allowing you to print if you're using Acrobat Reader, and not allowing you to select text, or at least when you do select it, it won't let you copy it. That ends up being just a UI implementation. There are other PDF readers, and those generally don't care. I'll also say that how this matters from a attack perspective is this ends up being yet another encryption scheme or a filtering scheme that you'll have to keep in mind when you're looking at it, and it's actually documented in the PDF spec. And I won't go diving into it too much here, other than to say that it exists and it's worth looking at. But this one ends up basically being another way to encode the data in a way where you have to do, you have to go and find the encryption key in order to decrypt it. So it provides all these features. As you can see, there's like a whole bunch of different features it provides. And a lot of these end up getting used in varying sequences in order to hide, say, what an attacker is attempting to do, what their objective is, from whoever might be analyzing the document. And the goal really is just to kind of try and slow down the defense and hopefully evade detection based upon any previous attacks or previous attack research. So another thing that we talked about some time ago was that the programmatic components of Acrobat Reader and like similar powerful tools provide a ripe arena for memory corruption exploits and that entire class of attack vectors. So what I'm talking about with that is obviously JavaScript. So you can write a document with any arbitrary JavaScript in it. It doesn't have too many limits on what you can do with the JavaScript, so if you can execute it in your browser, for the most part, you can execute it in PDF Reader as long as PDF Reader implements the same features and has the same JavaScript libraries in it. There's also additional features in PDF Reader that are PDF specific that your web browser doesn't have. The vulnerability, or I should say the vulnerable functionality, is typically reported to the public. So when the vendor or the government knows about it, or I think it's actually International Standards Organization now knows about it, they actually publish what they call a current vulnerabilities and exposures report and give it an ID number. So I picked two that I'm aware of. There's uncountably many, but I picked two that were just kind of worth looking into. So I was gonna, I probably did the thing where I loaded Firefox accidentally. I'll just close Firefox. So, here's one. So this ends up being a stack-based buffer overflow in cooltype.dll. So I can't remember if that's actually a separate DLL that's shipped with Acrobat Reader, or if it's a DLL that's actually compiled and linked into the original application. It tells you, say, what versions of Acrobat Reader are vulnerable. So you might be familiar with some of this stuff from the vulnerability assessment course. But it gives you also an explanation as to the level of severity. So allows remote attackers, if they've sent you the PDF, to execute arbitrary code or cause a denial of service or cause application crash. And even kind of a hint to how it's taken advantage of. So with a long field in a smart independent glyph sets or SING table in a TTF font. So as I exploited in the wild in September 2010. So another one, I think has less information. I kind of picked that just to show the varying level of stuff that's there. So this one basically just says Acrobat Reader. So this one actually works on more current versions of Acrobat Reader, including 10 and 11. Some of these actually implemented what Adobe called their smart sandboxing technology, which was supposed to load your PDF and your Java or JavaScript environment and the HTML parser inside of this little self-contained, what they called a sandbox. So this managed to actually escape from that functionality as well, so it had extra features in it to do that. So I can't remember the exact specifics about this one, but the other one, this one was basically a separate TrueTech font library that may not have originally been part of the project, was incorporated into the project to gain some additional benefit. This is a good example of code that was probably very safe on its own, and then Acrobat Reader, which wasn't really built to handle that code, now merged together, and a vulnerability was created because of unexpected, or I should say unexpected consequences of merging those two. So those are two examples. Browsing through that, so that the site that I'm actually going through here, this one, allows you to actually search for a lot of different things. So for instance, I can look for this. I can look for like CVE. I think that's another one that is popular. So this one's stack-based buffer overflow in Office XP 2003, 2007, 2010, 24, 2008 for Mac, Office for Mac 2011, and OpenXML file converter for Mac. Allows them to execute remote attackers execute arbitrary code via crafted RTF data. So cool thing about this one is that this one is successful not just on your Windows PCs, but also on Macs as well. So it supports like cross-platform exploitation. Now, whether the same exploit is going to work on both of them, I'm not sure. But, or I should say that I'm not sure if the same exploit code will work on both of them. But the vulnerability exists. The potential for it does exist on both of them. So. So those are some examples of exploits that are worth looking into, because when we are looking at these documents, it does help to understand what part of the code, what part of the program the attacker is probably trying to mess with. So now we get into really common exploit techniques involve memory corruption. I will say this is a little bit of a dated statement. It's becoming more and more popular, in my opinion, or from my observation, that we're seeing a lot more manipulation of macro languages and scripting languages and things like that that are built into applications. So not trying to break the application like some of those vulnerabilities I showed you were, but actually trying to use the scripting language to get the job done. Those tend to be a little bit easier to analyze than these. So a good example is that macro, the Visual Basic macro attack that I showed you in the Office document that we analyzed. In that particular case, it was really just trying to do a whole bunch of string concatenation operations to get the strings together in order to execute the code that it wanted to execute. In this case, what we're trying to do is we're trying to find a hole where the programmers of various applications actually did make a mistake, a logic mistake that causes you, if you give the application a specific unexpected input, to basically break the data structures underpinning the application and then result in being able to execute arbitrary machine code on the system. So that's the key distinction is in this case, we're actually trying to cause the application to start executing code that I wrote instead of code that the author of the application wrote. So 3 really common techniques that they're worth researching. I will go in and give I think the stack overflow or buffer overflow, I think there is a really good example that most of you are working on already in another class. But I think I have a link to that, so I'll make sure that I cross-link that. But the heap spray one you don't, so I have a good example in these slides of that. And then also some example reading. So I've always felt that understanding how to, and this is one of the reasons I started off the class talking about Metasploit and going through some of those examples, is learning how these things are built and learning what needs to go into building them is very helpful on learning how to take them apart after the fact. So I actually put a few links here of what I feel were really good examples that has been helpful to a few friends of mine for learning how to build some attacks. So I think this top one I think ends up building a PDF attack, and then this one right here ends up building a, if I remember correctly, it's an Internet Explorer based attack, so it's JavaScript and maybe HTML and Internet Explorer, and then I forget what the bottom one is, but they're from 3 different people. So they're kind of 3 different points of view. They're pretty good set. So I'd say I'm not going to go through these because it can easily take like 8 hours or something to get from the top to the bottom of these. But I would definitely recommend you try and follow these links when I get them up on the site and actually try and go through the sequence of steps. One thing too that I'll point out is that this one, the middle link here, that site has a large amount of really good in-depth tutorials on using a lot of these tools. And so this just ends up being part 1, which is kind of your introduction to stack-based overflows. I believe that I used some of that when I put together the one for another class. So, so for exploit walkthrough, what I'm going to kind of do is, step back for a moment, and rather than trying to go into, say, what a specific exploit does, in general, when someone's trying to exploit the Acrobat Reader application in order to get an outcome of executing arbitrary machine code, the exploits vary frequently from one to the next as far as what part of the application needs to be targeted, which means what JavaScript code or XML code or font code or anything like that needs to be embedded in the document. So the documents themselves will vary wildly. But just my observation of looking at a lot of these is that in general, and not saying all the time, but in general, the most common recipe is like these 6 steps. It's first, what I want to do is I want to make sure that while the application's running, working normally, and loading my document, that it is setting up memory with the desired shellcode in it, which means that the code that I want to execute on the CPU at some point in the future, I need to make sure that gets loaded into memory somewhere. There's a lot of different ways to do it. So I can embed it, for instance, in other objects, or I can have JavaScript code that builds it manually in memory. But at that point, the program itself is still running normally, and it's just executing normal code. Additionally, I may need to also litter a few breadcrumbs here or there, and those are basically little hints to the system to help instruct it where to find the code I want to execute. So those 2 things are generally like the first step. The next step is to cause the exploit or fault condition. So if you remember when we were looking at, I will go to this one that had a really good, now of course it's the one that, so this one had a really good description of what causes the fault condition, right? So this said that it allows remote attackers to execute arbitrary code, blah, 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 with a long field in a smart independent glyph sets table in a TTF font. So in this case, after I've gotten the PDF reader to load all that stuff in memory, I then want the PDF reader to load a TrueType font that's embedded in PDF, and that's one of the features that PDF has, is that since I want to be able to typeset my document based on the fonts I have on my computer, and then I send you the PDF, I don't want to also have to send you the fonts. So the fonts get embedded in the PDF as well, which means that the PDF reader has to be able to unravel those fonts. Well, it turns out that I guess there was a edge case that the programmer of cooltype.dll forgot to take into consideration when they're parsing one of the tables within the fonts. And I don't know what all this means because I'm not a typeface expert. But I'm sure that, you know, if I was reading this and I had, you know, a week or something, or a weekend, I could probably mess with one of those vulnerable versions of Acrobat Reader and mess with a PDF that has a TrueType font embedded in it to try and come up with, at the very least, a sing table that'll cause the application to crash. And when I get the application to crash, then I can start diagnosing what caused the program to crash. The program crashed because it was trying to access memory it was told to access memory that wasn't supposed to be accessed, or it wasn't intended to access, which means I had some sort of control over, or I had gained some sort of arbitrary control over what memory the application is trying to read in or write to or access or something. Or it might have tried to execute code somewhere that's junk, like random bytes somewhere. It might have transferred control, like jumped to an area of memory that doesn't have any usable instructions in it, which means I might have found a way to control where program flow moves to. So I might have found a way to control what address the next execution or the next instruction will be loaded from. So if I have that information, then maybe I can rewrite my attack. I can mess with my table to organize it in such a way so that I can predict where it's going to try and arbitrarily load a junk instruction from and make sure that there's not junk there. And so that type of mechanism is what goes into building an exploit. And then once you find one that works, you can cause this to happen, and then it may try and load memory from somewhere, or it may try and execute an instruction from somewhere. Not sure which, but one way or the other, you're going to cause the fault condition to then transfer control over to some instructions that you have left somewhere. So frequently, that's what happens in number 3. After you get that successful, then it transfers control from viewer application to what I would call breadcrumb code. And breadcrumb code is generally what I like to call little tiny bits of code that are executable instructions, but don't necessarily understand the environment they're running in. They don't know, say, what address they're located at. They don't know where they are in reference to other data in memory. And you can contrast that with normally compiled program code. So if I compile a program in Visual Studio and then I run it, that program always knows when it's running. It can make a whole bunch of assumptions about where stuff is located in memory because I compiled it that way and I told it where all the stuff was going to be loaded in memory. In this case, it doesn't know that. It's just executing arbitrarily out of some corrupted data structure that's in memory. So the breadcrumb code, the job of that is to try and query the processor and query the environment for some sort of information to try and learn more about it, to figure out what it can take advantage of, so what features exist in memory, how much memory exists to work with, and possibly where other data is located, to try and basically put together a trail to establish what I would call folder control over the execution environment, or basically make it adhere a lot more to like what compiled code would expect. Once you've got better control over it, you can start, for instance, interfacing with Windows API calls and things. So you can start calling the Windows system functions that are responsible for reading and writing files, or fetching stuff from the internet, or opening connections to the internet, things like that. And then finally, once you have that, then you have all the functionality you need in order to install a backdoor or some other attack code, and then eventually, if you want to, establish remote access, or what I would call interactive remote access, which is I type here on my machine and it commands the compromised machine, and then also persistence. So two big things that I want is remote access so that I can interactively work with that machine on demand, and then persistence, which is if the user decides they want to reboot their machine, or they want to drive across town to their friend's house, then when they turn it on at their friend's house, my backdoor reconnects. So I kind of break it up into these 6 steps because it kind of makes the most sense to me, and that pattern more or less ends up following with most of the exploits that I've seen, both in PDFs but also in like documents and even Internet Explorer and things like that. They all behave the same way because they're basically trying to load a big data structure with a whole bunch of complicated modules associated with it, and you're just trying to find one of those that has a vulnerability in it. So next I'll talk about a handful of what I would call the breadcrumbs, or the breadcrumb techniques that exist. So one of the more common ones is called the Sled, or sometimes called not Sled, just because the whole the no-op instruction, which is the byte for that is this one, the instruction code for it's that one, is basically an instruction that's supposed to be consumed by the processor with no effect. So, so a sequence of those will spend 10 cycles of execution doing nothing. So if you want to have a large, block of code that does nothing, then you can just fill it with this byte. So another variation I've seen, and why I typically just call it a sled, is say a sequence of what I would call inconsequential instructions. So ones like this where the register ECX, as we talked about, unless I'm actually doing some sort of control instruction or something like that, it doesn't really have any special meaning. So I can do whatever math on it that I want. I can change it as much as I want. So in this case, I can just keep, if I had the byte 41 10 times, then I would basically add 10 to ECX by the end of that. But the goal is that, I would move 10 bytes down the line. Or EDX is the same way. There's a whole bunch of other ones, or other ways that you can do it too. So these are all really common because in many cases, when you are exploiting, say, vulnerable part of an application, and you're trying to get control to transfer to your code, you might not be able to exactly predict to the byte where that execution is going to happen. That execution might only be something that you can guarantee to within a window of 10 bytes or 100 bytes or something like that. So if you can guarantee that, then what you can do is you can fill in so if you can guarantee that it's going to fall within a window of 100 bytes, if you were to make sure that you embedded 150 bytes of this character somewhere in your code, and then made sure that after that 150 bytes, that the next instruction was, actual functional code that you really wanted to execute that started doing the sequence of steps to actually give you control and download your backdoor and all that stuff. That would allow you to guarantee that your code always gets executed. So they call it a sled because what happens is you land anywhere within this region, and no matter where you land on it, you just slide forward. So if you land halfway between the beginning and end of your 150 byte sequence, then you have 75 more bytes to go until it starts executing the code you want. So it's a trick to be able to guarantee that that execution will always eventually end up at your code. You just can't predict the number of instruction cycles it'll take to get there. And that's because you can't predict exactly where in memory it's going to land, but when you experimented with breaking the parser, you were able to get it, within a 95% level of confidence or something, that it always would happen within this one, 100 byte or 150 byte window. So, and that ends up being a really common problem that you have to overcome just because of the dynamic nature of all the other stuff that's going on under the hood. Another common reason for this is, if you remember, we'll go back to here again. This one actually lists a bunch of different versions. So it has a bunch of different versions that this works for, this particular exploit. Depending on those versions, you may have had different features added and removed during their development, and that's going to shift, say, the landing point. So another one, sometimes called the Easter egg or just the egg, or canary, is that in some cases you may be able to successfully control it, so control, say, where that landing is, and it may be to a window where you have to have some sort of sled that ends up catching and directing the execution into the sequence of instructions that you want, or you might actually be able to guarantee that you will always land at this one spot in memory whenever you say return from the stack or return from an exception or something like that. However, you may run into problems where you only have maybe 500 bytes with which to build any sort of executable code in. So you can think of, for instance, when we were doing the malloc example before, you may have some sort of, there may be some arbitrary upper limit that's built into whatever feature you're trying to take advantage of. And that upper limit may just prevent you from being able to do that arbitrary code building beyond 500 bytes or something. So a common approach to solve that problem is to maybe embed in your document somewhere else. Maybe a really common one is to embed it within an image or within another subdocument or something, what I would call an egg or a canary value. And you already saw an example of that, but I don't think I called it that when we were looking at that exe malware. And that was the one that had the URLs which were prepended with strings of 11 bytes that looked like this. So if I take, say, an exe and I want to overwrite a really large section of a PNG or JPEG image with this exe data, normally if you would load that image, you just see a whole bunch of static, a whole bunch of junk data. It looks like the image got corrupted or something. And that's fine, the image viewer will either complain or not, depending on if the checksum matches. But what you can do with your code is it's very easy, and it takes a very small amount of bytes to write a loop that starts at the beginning of program memory and then works its way down until it finds the sequence of unique bytes, and this may just be one of them. And once it finds that sequence of unique bytes, it might then, just take a small amount of code for it to write the data following that into an exe file on disk, and then use Windows create process function to then load that exe file and run it. So you can embed an entire backdoor inside of some arbitrary object inside of your document if you can't fit that backdoor entirely within the exploit code itself. So it's a way of providing data or data space to your exploit if the window for code for your exploit is particularly small, like 500 bytes or 1 kilobyte or even 4 kilobytes. Generally speaking, for most exe files, you probably need more than like 8 kilobytes in order to have any real useful code in there, and probably far more than that. So the other thing, and the reason why you do need this canary value, is a lot of times the document objects are dynamically loaded, and sometimes they may even be loaded in a multi-threaded fashion. So it's kind of what order the document objects get loaded in might just happen at the the luck of the draw type of thing, or whatever the CPU scheduled them in. And if the ordering is not predictable or is not deterministic, then the location in memory where they're going to be, whether they're before your exploit code or after your exploit code, is also not predictable. So this type of approach helps you predict that you work off of the assumption that after my document's loaded, this value is going to be somewhere in memory, and memory is bounded. So I just scan memory for it, and then I wayfind from there. So similar to going back to a common like landmark in town or something like that, if you're in an area of town where you get lost or something. So so the last technique, at least for breadcrumbs, that I'll talk about is a heap spray, which is probably a really common term that you'll hear used. This can, and I'm going to, there's a whole bunch of different ways to do this, so I'm going to horribly summarize this and only focus in on one particular example, but there's a lot of different ways, and depending on the nature of the particular vulnerability you're targeting, what approach is used is driven by that. So I'm just going to give one, and then again, this class isn't about exploit writing, it's about exploit analysis. So the heap spray technique is similar to the not sled technique. It's actually kind of similar to a combination of both of the past ones, in my opinion. But it involves a brute force approach that attempts to fill up all memory or a significant portion of it with a repeating sequence in hopes that an exploit will more likely land in any one of them. One common approach that I've seen is to identify a small instruction that's also likely to address a memory location likely to exist in your target environment. So for like a real memory location, so one that's actually mappable. So for example, this value, if you were to convert that to int, then that actually maps to about 67 megabyte mark. Those of you who were kind of following some of my IDA Pro examples also probably noticed that a lot of program memory seems to frequently start maybe here at 400,000. Another common one is 100,000, or not 100,000, but whatever this is. 1 followed by 7 zeros. So there's a whole bunch of different ways to do it. 100,000, or 1 followed by all the zeros, ends up being whatever 4 gigs divided by 16 is. But the point is that if I try and allocate a whole bunch of memory to fill it up this way, then I might end up guaranteeing that I'm going to allocate memory that matches this particular address. So as you remember when we were walking through the dynamic allocation code, every time that we did a malloc to allocate more memory, it would typically allocate a successor, right? So it would allocate memory that was, a little bit further up from the last thing that we allocated, and keep doing that, keep doing it. So if you cause this to do it like 1,000,000 times or whatever, then eventually you might end up running into a situation where you have allocated memory that's close to this location. And then also another common approach to this is to make sure that that memory that's being allocated also contains this pattern. So really you just have to try and make sure that it contains this pattern. And the reason why you want it to contain that pattern is that you want to identify a pattern that's repeating, that's small instructions repeating. So in this case, it's a 2-byte instruction that evaluates to this. And one of the cool things about this particular instruction is that the second byte, so this one, is really just, it's a literal pulled from here. So if you happen to land and start executing code at an odd offset within this, then you end up basically adding AL, or adding to AL, whatever the next literal byte ends up being. Sort of a common approach is to maybe have something like this. You have instruction pairs, or I should say byte pairs for an instruction repeating that get you in a nice low memory range, and then also follow that up with like a series of no-ops or something. And the repeating sequence doesn't necessarily have to be this, but most of it can be filled with that. And then you can also possibly add like your own shellcode to it as well, in a little small section at the end of it. You end up running into a situation where you really are playing these statistical odds. So wherever your program happens to land within that window, or within any of those windows, the more of these bytes that you put in there, the more likely you are to land on code that you can control to lead into the exploit code that you're trying to get to execute. So I'm giving the presentation here, but there will be a large number of links and also some examples to accompany this when I do get it up on the website. So if I'm being a little bit general about it, I apologize. It is very difficult to demonstrate all this stuff without having the hands-on. But the goal of this is just that if I was to, if I was to cause this sequence of bytes to be written in memory in a lot of, in a repeating fashion, and a really good example of that is if I was to call a sequence of, a sequence of, or I should say, if I was to cause the application to call a sequence of data creation operations, for instance, creating new form elements or something like that recursively, the data structures that are created for that might actually populate this for me, that type of thing. So I can, using a sandbox, I can experiment with different ways to create this, some of which may be literally stitching it together with some of the binary building blocks that are in JavaScript, or writing XML code that actually ends up getting interpreted by the browser or by the PDF reader or by, maybe a Excel macros or some, Excel formulas that end up operating recursively as well. So the goal is to just basically try and fill up memory so that when you do take control of the program stack and you do cause it to jump to an arbitrary location in memory, there's a higher probability that it's going to land on a sequence of bytes like this. So, and as you would expect, if you end up sizing this for a if you end up sizing this for a system that has, or I should say, for an amount of memory that exceeds that the system has, you're likely to cause, PDF reader to complain that it ran out of memory or something. So those are some of the things to keep into consideration. So yeah. So the other benefit that you have, and this is what I call obfuscation. So you employ all that stuff to try and get control of the processor. It's very common then for you to have long sections of your document that could be interpreted as machine code. So a lot of signature detection was written to try and look for things that look like x86, x86 instructions sitting inside of binary data inside of a inside of a system. And I'll let's see. Well, I'll go through this and then pop this up. So there we go. So one approach that they have found is that you can be guaranteed two things if you're able to successfully execute that shellcode. Number one, that everything in there is executable, so all the instructions you put in there are going to be executed. Number two, unless you've done something to turn off the writability of that region of memory, that region of memory is still mapped as a writable region of memory, which means I can actually employ some, I hate to use the word, but like polymorphism to the code or something like that, or I have self-modifying code. So I can have, and this is actually very common up until very recent, on very recent versions of Windows and on very recent machines, was to have it set up so that you'd have a little tiny amount of code in there that would do the very basic things, and then it would go through and it would run a loop where it would then decrypt the following junk data, or what looks like junk data. It would decrypt it so that it was all executable, so that in the document you had on disk, you wouldn't actually have any executable code in it, or you wouldn't have a significant amount of executable code. So the amount of code that was executable was sized small enough so that it evaded detection, and then the code following it looked like junk to most of the automated systems. But then once it executed in the processor and in memory, all of the functionality was later on decrypted. So that's kind of one of the benefits that you run into with writable and executable code. And if you've been through like operating systems class or something like that, you probably have gotten a large amount of the insight as to why, from application management perspective, you don't want to have your executable sections of code writable. However, there's a handful of cases where that is still necessary. Some really good examples of those being like just-in-time compilers and things like that. They don't tend to run very fast or very well if they can't write and execute code from the same areas of memory. So, but I kind of listed off 4 like common next step type of things that your application, or I should say, you will try and get the application to do using your shellcode. So like attempts to load common Windows DLLs. So Acrobat Reader only loads the functionality Acrobat Reader needs. But if you want to use any other parts of the Windows API, you do have that at your disposal. You just need to tell Acrobat Reader to load more DLLs that have those support code in it. Likewise, you may also not have access to where the Windows API functions have been mapped in memory. So you may have to go looking for those and try and enumerate them, try and basically store all the different WinAPI function addresses after you look them up in a lookup table for yourself so that you can refer to them in the future. Attempts to build data structures to provide to those calls as well. And then like a really good example that I've seen commonly is instead of delivering 500 kilobyte executables embedded within a document, what a lot of times people want to do is keep the shellcode small, basically keep all the, what I would call the defect code, right? All the code that's not actually part of a legit document. Keep that small and concise. And one way to do that is to get it just to the point where it can download something from the internet, and then don't do anything else special. So then you get the document, or I should say you get Acrobat Reader or whatever, to go and download something from the internet, and then use create process to execute that from disk. And then that takes over from there. But even those things, so the more functionality that you embed in the shellcode, the more likely it is to be identified as an illegitimate part of a document. So using this obfuscation technique is one way that they were able to try and overcome it and make it look like the data in there is just random compressed data or random image data or something like that. So I'll also talk through some recent mitigations. A lot of the techniques that I discussed are old, but technology's improved quite a bit on our side, and the effectiveness of those techniques has been largely marginalized. So Windows 10, if you're running Windows 10 on a new system and you haven't taken it upon yourself to disable a lot of the security mitigations they have built into it, and you may even have added some or installed antivirus, or that may have come shipped with your system, then you're probably enjoying all three of these plus others. And so one of the critical ones, and this one was designed squarely to try and end, and it hasn't been comprehensively successful, but it's been largely successful, basically trying to end this and a lot of these techniques that I talked through here. So every single one of these techniques had one thing in common, which is I have code that I want executed, and I need that written into memory. And I need it written into memory by something other than the normal Windows operating system. So I need my document to actually make the document viewer write that to memory, which means that it needs to be able to execute code from writable memory. Well, with the newer processors, especially the ones that are built on the 64-bit platform, this isn't a benefit that has anything to do with how many bits it's using, but they decided to employ an additional technique, which was to restrict mapping of memory so that you can basically do what they call write, and this is supposed to be typically the XOR or the NOT, depending on how you want to look at it, but write, not execute, or write, XOR, execute. So you can have memory that's mapped to be either writable or executable, but never both, with the exception of the handful of special cases that the Windows operating system itself uses. So, if Windows needs to run an executable or a DLL, it does need to load that from disk into memory. So it doesn't need to read those pages from disk into memory before it can execute them. But what it'll do is it'll read those in, and then it will remap the memory to be executable and not writable after it does that. And then from then on, all the memory that is mapped in as writable will be actually checked at the processor level every time the instruction pointer is pointing at, or as I should say, pointing the processor to fetch an instruction. It'll actually make sure it's not trying to fetch from writable memory. So it's a special feature that's in a lot of the newer CPUs that's designed specifically with a lot of the use cases we just discussed in mind. So another one is called address space location randomization. And to be honest, this is one that this is one mitigation that is older, and some of the heap spray techniques actually were employed to try and get around this mitigation. But it works relatively well for many of the exploits, especially the older ones. And what it does is, if you remember when we looked at when we used objdump to look at the exe, there's actually some hints in there as to where in memory the exe wants to load its sections. And the DLLs have those hints as well. So they say, I want my base address to be, 400,000, or 1 followed by 7 zeros, or 2 followed by 7 zeros. So they say they want their address space set up in a certain way. What this says is you can employ some mitigation that may sacrifice some performance in exchange for no longer having that predictability. And then likewise, also with the dynamic memory allocation, so using malloc or free or new and delete, those things also may get a certain amount of non-determinism injected into them. And some of you may have run into that if you were working on the vulnerability assessment, the buffer overflow project that was in there. There is specific instructions that turn off a handful of features in the operating system, and that was one of them. And then finally, stack smashing protection uses, there's the word canary again, but it uses canary values, in this case for good reason, in that if you remember your stack or your argument heap, or your local variable heap, whatever you want to call it, that's set up in a certain way so that your program injects special, what I'd call canary values in certain boundaries of the stack, where when your program was authored, you can predict where the stack shouldn't be modified. So where I should say the beginning and end of various regions of the stack should be. So canary values are injected in there so that at various changes in control flow, so return from a function call or entering a new scope, any sort of, if you think any sort of like braces type control flow change for your program, the compiler will actually add extra checking logic or validation logic in there to try and see, or even the operating system may introduce it as well, to try and see if these canary values have disappeared. So if the value that's supposed to be there throughout the lifespan of the program suddenly disappears, that means something overrode it when I was told that nothing should overwrite it. Which means there's probably a logic bug in there that someone found, someone overrode it, and what'll happen, and if you didn't turn off the stack protector on the vulnerability assessment project, then you would run into this, is that as soon as you try and commit the buffer overflow, it'll detect it, and then it'll complain to you. It'll actually say stack smashing detected or something like that. And so what it'll do is it'll basically kill the program. And once the program's killed, any of the arbitrary code that was injected is going to be killed along with it too. And it's all going to be returned back to the caller.